Hey everyone. With new AI models dropping what feels like every single week, it's easy to think we're just getting slightly different versions of the same old thing. But today, we're going to pop the hood and really explore the fierce battle of ideas that's happening deep inside these large language models. Okay, so let's just get right into it because it's a really good question. You look at the latest models, Llama 4, DeepSeek V3, and architecturally, they look a lot like models from a few years ago. It kind of feels like we're just polishing the same engine. So, are we hitting some kind of innovation wall, or is the real action happening somewhere we can't see? Well, the truth is, the innovation is absolutely happening, but it's not about totally reinventing the wheel. It's more like a high-stakes engineering game. Architects are making these crucial trade-offs, picking and choosing from a whole toolkit of clever solutions to solve these fundamental problems of cost, speed, and raw performance. All right, so let's treat this like a puzzle. How exactly are today's top architects building these incredibly powerful, yet surprisingly efficient models? We're going to open up that very toolkit by breaking down three core challenges. We'll look at the clever, sometimes subtle solutions that engineers are using to win this battle under the hood. First up, let's tackle the first big challenge, the attention bottleneck. This is all about taming the enormous computational cost of letting a model actually understand long stretches of text. You see, self-attention is the secret sauce. It's the magic that lets an LLM figure out which words are important in a sentence. But for that to work, the model needs a kind of short-term memory, which is called the KV cache. Now, here's the problem. With a really long documents, this cache just explodes in size, eating up all the memory and creating a massive bottleneck. So the first tool that pretty much everyone grabs now is Grouped Query Attention, or GQA. It's become the new industry standard for a reason. Instead of every single part of the model needing its own little memory slot, GQA cleverly groups them together so they can share. It's a really simple, elegant trick that shrinks that KV cache way down without really hurting performance. Now, DeepSeek V3 takes a slightly different approach with something called Multi-Head Latent Attention. Think of it like a three-step dance. First, it takes all that key and value information and compresses it into a tiny little summary. Second, it stores only that compressed summary in the KV cache. And third, right at the last second, it blows it back up to full size. It's a classic engineering trade-off. Use a tiny bit of extra compute to save a huge amount of memory. And then there's another really smart idea, used in Google's Gemma 3, sliding window attention. It's based on a really simple question. In a 100,000-word document, does the last word really need to pay attention to the first word? Probably not. So, this technique just limits each word's view to a smaller, local window of its neighbors. It's just common sense, and it drastically cuts down on both memory and compute. Okay, on to our second massive puzzle, and it's a big one. How in the world do you get the raw knowledge of a giant model without the absolutely crushing cost of actually running it? 671 billion. Just let that number sink in for a second. That's the total number of parameters in a model like DeepSeek V3. That's how it holds so much knowledge. But the question is, how do you make something that big practical to use? And that right there is the fundamental dilemma. To be really, really smart, these models need to be huge. But running a model with hundreds of billions of parameters for every single sentence you generate, it's just not feasible. It's way too slow and way too expensive for almost everyone. The solution that has completely taken the industry by storm is the Mixture of Experts Architecture, or MOE. Think of it this way. Instead of one giant generalist brain that has to do everything, you have a massive team of specialists. And for any given problem, a smart router just picks the 2 or 3 best experts for that specific job and puts them to work. So, and this is the really incredible part. While the full DeepSeek V3 model has 671 billion parameters on paper, when you're actually using it, it only activates about 37 billion of them at any one time. This makes the model sparsely activated. You get the knowledge of a gigantic model, but with the running cost of a much, much smaller one. It is an absolute game changer. And of course, architects are already refining this idea. DeepSeek V3 uses a clever twist called a shared expert. This is one specialist that's always active, and its only job is to learn the really common stuff that appears everywhere, like grammar and punctuation. This frees up all the other experts to get even better at their highly specialized tasks. It just makes the whole system more efficient. All right, on to our final challenge. This is one that often goes unnoticed, but it is absolutely critical. The sheer nail-biting difficulty of just keeping these massive training runs from completely falling apart. Trying to train a model with billions of parameters for weeks on thousands of GPUs, it's like trying to balance a skyscraper on the tip of a needle. It is incredibly unstable. The math can just explode at any moment, causing the entire training run to collapse. And that means wasting millions of dollars and months of work. The next tools in our toolkit are all about stability. A key tool here is called normalization. But what's so fascinating is that it's not just about using it, it's about where you put it. For years, the standard was pre-norm, placing it before the main processing blocks. But the team behind a model called OLMO2 found that a unique kind of post-norm, placing it after the block but still inside the residual connection, led to much smoother, more stable training. A tiny, subtle change with a huge impact. And another one of these stability heroes is QK-norm. This is an extra super targeted normalization layer that's applied directly to the query and key vectors right inside the heart of the attention mechanism. You can think of it like adding a precision shock absorber to the most volatile part of the engine just to keep everything running smoothly. Okay, so let's step back and see what this all adds up to. It's pretty clear that building a modern LLM isn't about searching for one single perfect architecture. It's really an architect's balancing act. There is no magic bullet. Building a great model today is about artfully choosing and combining these different tools. Do you need maximum memory efficiency, or do you need raw speed? Do you need the massive knowledge of a mixture of experts model? Every single choice is a trade-off, balancing performance, cost, and speed. So there you have it, the modern LLM Architects Toolkit. We've got powerful solutions for efficient attention, like GQA and sliding windows. We've got clever ways to get big model smarts with a small footprint using mixture of experts. And we've got those unsung heroes, the normalization techniques that keep the whole fragile process from falling apart. Every single one of these tools was invented to solve a very specific, very difficult engineering problem. And that leaves us with one final fascinating question to think about. As we push these models even further, what new unforeseen challenges are waiting for us around the corner? And what brilliant new tools will the next generation of architects have to invent to solve them?